Okay, so we've just seen an alternative method to Gauss elimination. We've seen the limitations and the advantages of using Jacobi's method to solve this system of linear equations using the idea of iteration. And basically we took this system of linear equations and we rewrote them in terms of x1, x2 and x3 to form this. And basically the idea is that the numbers on the left were our new values, and the numbers on the right were using our original values or our old values of x1, x2 and x3. And basically the idea is we just kept doing this iteration where our new values became the old values and so on, okay? But the thing is, this is the issue which I have with Jacobi's method. When we use that first equation to get a new updated value of x1, didn't we say that newer values are nearly always more accurate than the old values, okay? Well, the reason why I say nearly always is because we might have a situation whereby we have a diverging away from the true solutions, but we've discussed the limitations and how we can rectify that in the previous video. But my idea is that in general, the new value of x1 will always be more accurate than the old value. So why then, with Jacobi's method, when we moved on to try and calculate x2, did we continue to use the old value of x1? Because we've just said, look, we've got a better, more accurate version of x1 now because we've calculated it in the top equation. Why then are we continuing to use that old value of x1? And likewise, when we move on to calculate x3, we now have a newer, more updated, more accurate version of x1 and x2. Why then did we continue with Jacobi's version to use those old values which we know are less accurate in general? So this is where the Gauss Seidel method comes in. It's basically an adaptation of Jacobi's method, and it literally just says, look, I want to, when I get to x2, use my newer, improved value for x1 in here. And likewise, when we get to x3, I'm going to be using my new improved values of x1 and x2 in here to calculate x3. So hopefully we should be able to get to the solution or converge to a solution quicker. So let's just illustrate this. Let's going to start with the x1, x2 and x3 being zeros as we did before. So those are my initial values. So x1, x2 and x3. I'm just going to start off with them all being zeros, just like I did before. And let's plug it in and let's see what it becomes. Okay, so I'm going to start off with x1. So x1 becomes 21 minus 4 times 0 minus 0, all divided by 10. So in which case, that comes out as 2.1. So that doesn't change, but that's not expected to change because this is exactly the same as Jacobi's at this stage. Okay, but this is where it's different for Gauss Seidel, because when it comes in for trying to calculate x2, I'm going to be using my new value of x1. So I'll have 51 minus 2 times, well now instead of using my old value of x1, instead I'm going to be using this new improved 2.1 version of x1. So in other words, I'll just stick in 2.1 in here, minus 3 times, well I haven't got a new improved version of x3, so I'm still going to stick that as 0, my original guess, all divided by 20. And if I calculate that, that comes out as 2.34. Okay, and finally, if I do my x3, well, I now have new improved values for x1 and x2, so I'm going to be using those. So 37 minus my new improved value for x1, which is 2.1, minus 3 times my new improved value for x2, which is 2.34, divide all of that by 10, and that comes out as 2.788. All right, great. So that's my new improved value for x3 as well. Okay. And then basically, I won't bore you with the steps, but I can keep now doing that same process again. So every single time I'm using the most recent or most up-to-date value which I have for either x1, x2 and x3. Okay. So in fact, if I do this again, I find that the next step comes out as 0.8852 for x1, 2.04328 for x2, and 2.998496 for x3. And in fact, if I do it one more time, I find it comes out as 0.9828384. 2.0019418 for x2, and 3.0011336 for x3. So the first thing to notice here is that thinking back to Jacobi's method, if you made notes, you might want to bring those up and have a look at them. After 3 iterations, I end up with saying that, look, x1 is going to approximately be around 1, x2 is going to be approximately 2, and x3 is going to be approximately 3. In other words, it converges far, far quicker than Jacobi's method, okay? However, just like Jacobi's method, we need to be aware that it may also diverge as well, and it's exactly the same condition for divergent. We basically need the case that the diagonals are dominant. In other words, the sum of all of the other elements on that row, of course absolute values, so we don't get cancellation. When we add them all together, if that is less than whatever that diagonal element is, we can be confident it's going to converge, okay? It's going to converge eventually, okay? But my point is, it converges far, far quicker than Jacobi's method. The reason being is because we're using as many up-to-date values as we can, rather than waiting until the next step before we use those new updated values. Okay, so if we want to think about the comparisons between Gauss Seidel, which we've just seen, and Gauss elimination, okay, very, very kind of similar comparisons that we can make for Jacobi's method, okay. So basically, the first thing to say is that Gauss Seidel does not modify A, okay. So A is not modified. Just like it is with Gauss elimination, A is modified in order to form that upper triangular matrix, then use back substitution or something. Okay, with Gauss Seidel and Jacobi, we don't have to modify A at all, which is great because it means that we don't have to worry about storage of elements or things like that when it comes to really big sparse matrices, okay? The other thing that we can make advantage of when we're thinking about Gauss Seidel, and actually this is certainly true to some extent of Jacobi's as well, is that we can make use of the fact that we have a sparse matrix. So if we have a really, really big matrix that is sparse, in other words, we have lots of zeros in our coefficient matrix, we can really make advantage of that on the basis that the way which we're calculating our equations will basically have coefficients with zeros in. Okay, so because we're going to have coefficients with zeros in, we can basically take advantage of that on the basis that we're not going to have many operations that we end up doing. Okay, so sparse matrix means fewer operations, whereas we can't make use of that when we're talking about Gauss elimination, right? Gauss elimination is adding or subtracting one row for the other. If it is equal to 0, we may end up changing that element from 0 to a non-zero element, okay? Whereas with a sparse matrix with Gauss Seidel, and also to a certain extent with Jacobi's, if we have a sparse matrix, it means there's fewer operations that we need to worry about, okay? The other thing that is really good about Gauss Seidel rather than Gauss elimination is the fact that it converges to a solution really quickly. Okay, so it will converge faster, and in fact it will converge faster than Jacobi's and also Gauss elimination as well. So if you want one that's going to converge quicker, again, we said one of the limitations of using Gauss elimination is that time penalty. It's quite cost heavy in terms of time. Then because Gauss Seidel actually converged relatively quickly, we've overcome that issue with that time as well. Okay.